The process of producing a fabric by interlacing warp and weft threads is known as weaving. The machine used for weaving is known as weaving machine or loom. Weaving is an art that has been practiced for thousands of years. The earliest application of weaving dates back to the Egyptian civilization. Over the years, both the process as well as the machine have undergone phenomenal changes. As of today, there is a wide range of looms being used, right from the simplest hand loom to the most sophisticated power loom. The power loom was a steam powered, mechanically operated version of a regular loom, an invention that combined threads to make cloth. A power loom differs from hand loom in a few respects, such as construction of loom, method of operating, different motions of weaving. It works at high speed, aiming at high production. This loom has all three motions wise: primary, secondary and auxiliary motion, with iron thread for compactness, that is strength. The strength is required to resist shocks and vibrations resulting from several mechanisms of weaving. The power loom with iron consumption gives an increased speed and production. A power loom, once started, runs continuously till the supply of pin in the shuttle is exhausted. The production of power loom is 3 times more than that of hand loom. In 1785, Edmund Cartwright patented the first power loom and set up a factory in Doncaster, England to manufacture cloth. A prolific invention, Edmund Cartwright was invented a wool combing machine in 1789. Continued to improve his power loom, invented a steam engine that used alcohol and a machine for making rope in 1797, and aided Robert Fulton with his steamboats. Cartwright's power loom needed to be improved upon, and several inventors did just that. It was improved upon by William Horrocks, the inventor of the variable speed baton, and American Francis Cabot Lowell. The power loom became commonly used after 1820. In order to interlace warp and weft threads to produce a fabric, the following mechanisms are necessary on any type of loom: primary mechanisms, secondary mechanisms and auxiliary mechanisms. Primary mechanisms. These are fundamental or essential mechanisms. Without these mechanisms, it is not practically impossible to produce a fabric. It is for this reason that these mechanisms are called primary mechanisms. The primary mechanisms are 3 in number: shedding mechanism, picking mechanism, beat up mechanism. Coming to the shedding mechanism, separation of warp threads into 2 parts, that is upper and lower layers for the easy movement of shuttle to lace a weft yarn in between the warp threads is called shedding, or it is the process of separating the warp threads which run down the fabric into 2 layers to form a tunnel known as shed, and shed is produced by means of heedles. Sheds should not be too but sufficient for the shuttle to pass through comfortably with excessive frictional resistance. Shuttles in silk looms are generally smaller than those used in cotton looms. The length of the wall between the back rest and the hand should be greater than that used in cotton looms, as this reduces strain on the warp in shedding and tendency for making starting pace. Coming to the picking mechanism, passing of webbed thread from one sleeve to another through the division of warp threads is known as picking. It is done by giving a lateral motion to the picking handle and thereby driving the shuttle across the shed. A shuttle is used for picking in hand loom and also in conventionally automatic looms. From the point of view of cleanness, free from oil stains and the avoidance of weft blocking in the woven cloth, underpick motion is preferred to overpick mechanism in the weaving of silk. Coming to the beat up mechanism, pushing the newly inserted weft into the already woven fabric at a point known a fell is called beating up. It is done by reed. A slave moves forward to beat up the last pick and weft and goes backward to allow a shuttle pass through the warp division. These three primary motions are done manually in hand loom and by means of various mechanical devices in power looms and automatic looms. Coming to the secondary mechanisms, these mechanisms are next in importance to the primary mechanism. If weaving is to be continuous, these mechanisms are essential. So, they are called the secondary mechanisms. They are take up motion, let off motion. Coming to the take up motion, the motion withdraw fiber from the weaving area at a constant rate that will give the required pick spacing and then winds into a roller. Modern silk looms are built with ranging dimensions taken up rollers which provide sufficient surface contrast to resist slippage under normal conditions. Coming to the let off motion, the motion delivers warp to weaving area at the acquired rate and at constant and suitable tension by unwinding warp threads from warp beam or flange tube. Coming to the auxiliary mechanisms involved in the power loom, to get high productivity and good quality of fabric, additional mechanisms called auxiliary mechanisms are added to a power loom. The auxiliary mechanisms are used but not absolutely essential. This is why they are called auxiliary mechanisms. These are warp protector mechanism, weft stop motion, temples, brake, warp stop motion. This will found in the automatic looms. Coming to the warp protector mechanism, the warp protector mechanism will stop the loom if the shuttle gets tapped between the top and bottom layers of the shed. It thus prevents excessive damage to warp threads, reed wires and shuttle. Weft stop motion. The object of the weft stop motion is to stop the loom when a weft thread breaks or gets exhausted. This motion helps to avoid cracks in a fabric. Temples. The function of the temples is to grip the cloth and hold it at the same width as the warp in the reed before it is taken up. Brake. The brake stops the loom immediately whenever required. The weaver uses it to stop the loom to repair broken ends and picks. Warp stop motion. The object of the warp stop motion is to stop the loom immediately when a warp thread breaks during the weaving process. Figure 1 shows the passage of a warp sheet and cloth through a plain power loom. A warp sheet A from a weaver's beam B passes around a backrest C and is led around Lees's rod D to help shafts E and F, which are responsible for separating the warp sheet into two layers to form a shed. The purpose of the backrest and the Lees rods is to separate the warp yarns uniformly and precisely and reduce entanglement and tension in the yarns during the opening of the warp shed. The warp yarns then pass through a reed G, which holds the yarns at uniform spacing and is also responsible for beating up the weft yarn I into the fell of the cloth. After the weft is beaten up, the warp yarns interchange positions in the shed and thereby cause interlacing to be achieved. At this point, cloth is formed and is held firmly by temples J to assist in the formation of a uniform cloth. The cloth H then passed over a front rest K around an emery roller or take-up roller L and a guide roller M and is finally wound onto a cloth roller N. Motion of head, shaft, shuttle and sleigh. In a plain power loom, the head, shafts, shuttle and sleigh are operated by mechanisms that are set in motion by a motor through a crankshaft and a bottom shaft. The heeled shafts move up and down by the shedding mechanism. The motion is obtained from the bottom shaft or counter shaft that carries the toppets. So the warp sheet is divided into two layers and it forms a shed. The shuttle is pushed into the warp shed by a picker that gets activated by a picking mechanism. Normally, shuttle is kept in a shuttle box. When the shuttle is pushed, it reaches the opposite box. The arrival of the shuttle in the opposite box confirmed by shuttle checking devices. The picking mechanism is set in motion by the bottom shaft. The crankshaft operates the sleigh through the crank and crank arms. The sleigh gets to and fro motion as the sleigh reciprocates. The reed, which is fixed to the sleigh, also gets a to and fro motion. The reed thus beats up the weft into the fell of the cloth. Warp and cloth control. The shuttle is pushed into the warp shed by a picker that gets activated by a picking. After beating up the weft into the fell of the cloth, a take-up motion draws the cloth forward and winds it onto a cloth roller. At the same time, the warp is delivered from the weaver's beam by a let-off motion. Stop motions. To ensure good productivity and quality of cloth, the following stop motions are used. The warp protector mechanism protects the warp from breakage during shuttle trap and stops the loom immediately. The weft stop motion stops the loom if a weft thread breaks or the weft yarn gets exhausted and thereby prevents the formation of weft way cracks in the fabric. The break stops the loom instantaneously at any desired moment. The warp stop motion stops the loom when a warp thread breaks during weaving. Power loom are driven by the following types of drives: individual drive and group drive. Coming to the individual drive, in this method each power loom is driven by an individual motor. The power required to drive a plain power loom is 0.75 HP in a simple driving arrangement commonly found in mills. A single motor is used to drive the loom. Motor A via motor pulley B and looms pulley are fast and loose pulley C and D drives the top shaft or crankshaft E. A crankshaft gear wheel F and a bottom shaft gear wheel G drive the bottom shaft H. By means of a starting handle, a belt fork can be used to change the position of the belt on the fast and loose pulley arrangement. When the belt is on the loose pulley D, the pulley will rotate, but the crankshaft will not rotate. Therefore, machine can be stopped. By moving the belt to the fast pulley C, the loom can be started or stopped at any time. Speed of the crankshaft can be calculated by the motor speed into 960 into 120 revolutions per minute. The speed of the bottom shaft can be calculated speed of the crankshaft into 120 into 60 RMP. The ratio of the number of teeth on the gear wheel, that is the ratio of the number of teeth on the crankshaft gear wheel to that on the bottom shaft gear wheel is 1:2. The actual number of teeth in the two gear wheels could be 36:72, 45:90, etc. Since the ratio of the number of teeth on the gear wheels is 1:2, the ratio of the speed of the crankshaft and the bottom shaft will be 2:1. If the crankshaft has a speed of 50 RMP, the bottom shaft will have a speed of 25 RMP. When the crankshaft makes one revolution, one pick is inserted. If it has a speed of 75 RPM, 75 picks will be inserted in a minute. Therefore, the crankshaft speed in RPM also indicates the picks per minutes. That is, a crankshaft speed of 75 RPM indicates a pick insertion rate of 75 ppm. Crankshaft speed indicates the loom speed. Coming to the group drive, in the decentralized weaving sectors, a group of looms is driven by means of a common motor and an overhead shaft and belt drive arrangement. This method of driving power looms is found in the decentralized weaving sections. It can be seen in common motor. A drives an overhead shaft D via pulleys B and C, while is in fact the main shaft of the system. The main shaft runs from one end of the loom shed to the other. A number of pulleys E are fixed on this shaft, one for each loom. Each loom has fast and loose pulley G, which is connected to the corresponding main shaft pulley by means of a belt F. The belts can be shifted on the corresponding fast and loose pulley either to run the loom or to stop it. Looms are classified mainly into hand looms and power looms. The power looms are classified further into the following categories. Non-power looms. These looms have only the basic mechanism, vice, primary, secondary and some auxiliary mechanisms. The following are examples of non-automatic power looms: tuppet looms, Dobby looms, jacquard looms, drop box looms, terry looms. Coming to the automatic looms. To get high productivity and good quality of fabric, additional mechanisms are added to ordinary non-automatic power looms. These looms are becoming popular because of their advantages of versatility and relative cheapness. Coming to the shuttle-less looms or unconventional looms. In the non-automatic and automatic looms, shuttles are used for inserting the weft yarns. In these shuttle looms, preparation of weft yarn and the weft insertion mechanism itself limit the loom production and fabric quality. They are also prone to mechanical problems in propelling the shuttle. Hence, loom manufacturers have developed looms with various innovative and alternative means of weft insertion. These modern looms are known as shuttle-less looms, and some examples of the looms are air jet loom, water jet loom, projectile loom, repair loom, needle loom, and various other methods include rectilinear multiphase looms. Coming to the circular looms, these looms achieve higher weft insertion rates because more than one shuttle is delivered at a time. In these looms, the shuttle move simultaneously in a circular path and tubular fabrics are produced. Advantages and disadvantages of different loom drives. Coming to the advantages of individual drive are listed below. In case of motor of any particular loom fails, that loom alone will stop running while all the other loom keep running. Power losses in individual loom drive are much less than the losses in a group drive system. There is therefore considerable saving in power. The life of the transmission belt is comparatively greater in individual drive. In the individual drive system, there will be a clear view of all looms in the shed due to the absence of a overhead shafts and moving belts. The lighting in the shed will be brighter and more uniform. The possibility of accidents is considerably minimized in the individual drive system, as each loom and its drive is compactly arranged without any interloom connection. The shed plan and layout of loom is neat and easy. The disadvantages of individual drive are: initial cost is high, high maintenance cost is required. Coming to the advantages of a group drive, initial cost is low, high maintenance cost is required. Disadvantages of group drive: high power consumption, one motor drives a number of looms, so if it is fails, all the looms it drives are affected. This result in poor loom shed efficiency. There are greater chances of accidents due to the overhead and other interloom connections. The large number of pulleys and belts in the loom shed will reduce the effective amount of light in the loom shed. The layout of a group drive system is complicated and presents a clumsy overall appearance. The textile industry possesses a significant status in India's economy. Power loom weaving process is a most important and inevitable factor which plays a key role in making textile industry able to flourish successfully and provides it a stout competitive commercial industry base.